Hello to all electronics and sound engineering enthusiasts. In this episode of our headphone components review series, we are going to focus on one of the most crucial and sensitive parts of the device, the speaker driver. This is the component that ultimately delivers sound from the electronic circuit to your ears. Today we'll explore different types of drivers, the technologies used in them, and how these tiny details determine the sound quality and character of headphones. If you're passionate about audio engineering and component design, this video is made for you. So, common types of headphone drivers. There are several types of drivers in wireless headphone speakers, but I will only mention 3 of them here. Yes, we have it. At the first, we will speak about dynamic driver. Still the most common type in wireless earbuds like AirPods or Sony. Monitors diaphragms usually 6 to 10 mm design to fit inside in-ear headphones. They made of graphene or lightweight polymers for reduced weight and improved frequency response 20 Hz to 20 kHz. The next one is planar magnetic driver. What is that? Used in high-end wireless over-ear headphones. Flat diaphragm with a magnetic array for highly accurate sound due to their size, mostly found in larger headphones. And the last one is balanced armature. What is that? Popular in wireless IEMS in-ear monitors, like Sennheiser Momentum True Wireless. It has some special features and they are 1. Extremely small size, 2. Focus on high frequencies, and 3. Ideal for multi-driver design. Now, one of the key factors in headphone design is the size of the audio driver. The driver size plays an important role in how different frequency ranges are produced. In most in-ear headphones, the driver diameter typically ranges between 6 to 10 mm. But we should have a note here. In the headphone we are analyzing, the exact diameter of the driver is unknown. Also, labels such as C7, as you can see here, and C3, as you can see here, seen on some parts are factory production codes or mold identifiers and do not represent the actual driver size. What's the difference between larger and smaller drivers? Larger drivers, for example around 7 to 10 mm, they tend to produce deeper and more powerful bass because their bigger diaphragm move more air. This makes them ideal for reproducing low frequencies, 20 Hz to 200 Hz. Smaller drivers, for example 3 to 5 mm, these offer greater detail in high frequency range, 2 kHz to 20 kHz, and are often used in dual driver designs, one for bass and one for treble. So driver size directly affect bass response, sound clarity, and overall frequency performance of the headphones. Now we came to technical design parameters of drivers. What are that? Yes, you can see it. At the first, we have impedance, determined by coil design and number of windings. Impedance affects the current flow from the source, like a phone or an amplifier. Common headphone impedance are between 16 and 80 ohms. Lower impedance 16 to 32 ohm works better with low power devices but may sacrifice accuracy, while higher impedance 64 ohm or more requires an amplifier, usually seen in stereo headphones. The next one is power. Maximum input power is set by coil heat, tolerance, and diaphragm material. It represents the maximum electrical energy a driver can handle without damage. Most headphones operate between 10 to 100 mV. For these drivers right here, likely around 20 to 50 mW, though it varies by design. So, the next part is sensitivity. What is that? Indicates sound output per unit of input power. Lighter diaphragms and stronger magnets increase sensitivity, typical 90 to 120 decibel per milliwatt. And the next one is frequency response. What is that? Range typically 20 Hz to 20 kHz, influenced by diaphragm shape and housing. Larger diaphragms emphasize bass 20 to 200 Hz, while smaller ones enhance treble 2 kHz to 20 kHz. Now we came to main structure and design components of dynamic drivers. So, dynamic drivers are made up of several essential components, each carefully designed and engineered. Now you can see it, yes. At the first we have diaphragm, as you can see in my hand and here. Yes, we have it. Okay. A thin flexible membrane that vibrates to produce sound waves. Typically made from lightweight polymers like polyethylene, terephthalate, graphene, titanium, or beryllium. The choice of material depends on weight, flexibility, and frequency response. For example, graphene is used in high-end diaphragms due to its high strength to weight ratio and excellent acoustic properties. And shape and size about diaphragm. Diaphragms are usually circular or conical. The size, for example, 3 mm or 7 mm, directly affects the volume of air displaced and the frequencies produced. A conical design increases vibration amplitude, improving bass performance. And we have also surrounded suspensions. The aids of the diaphragm, typically made from rubber or foam, control the diaphragm's movement and help prevent distortion during operation. The next part is a voice coil. The voice coil is right here. You can hear. A coil of wire attached to the diaphragm. When an electric current passes through the coil, it moves within the magnetic field. Typically made from copper wire or copper-clad aluminum wire CCAW for a balance of lightness and conductivity. Number of windings. The number of turns in the coil affects driver impedance and sensitivity. The design of this component is based on precise electrical and magnetic calculation. And connection to the diaphragm. The coil is connected to the center of the diaphragm and its movement must remain perfectly aligned to produce uniform, accurate vibrations. And next part is magnet, a permanent magnet that generates a magnetic field to interact with the voice coil, most commonly made from neodymium due to its high magnetic strength. Some professional drivers use ferrite or samarium cobalt magnets. Magnets are usually circular or cylindrical. The strength of the magnetic field measured in Tesla influences the force generated by the coil. The magnet's design must be well matched to the voice coil for optimal efficiency. And now you can see some teeny holes right here and right here. I hope you can see it. Why are there teeny holes in drivers? At the first, air pressure regulation. These holes allow the diaphragm to properly manage air pressure as it vibrates. Without them, unbalanced pressure could restrict diaphragm movement, leading to muffled or restricted sound. The second cause is resonance reduction. The holes act as part of an acoustic system to minimize unwanted frequencies that could degrade audio quality. And the last one is prevention of blockage. In in-ear headphones, the holes prevent air or moisture build up behind the diaphragm, maintaining constant sound quality. And note, the number, size, and placement of these holes are carefully calculated based on acoustic engineering and flight dynamic to optimize the driver's frequency response and maintain a balanced sound across bass, mid-range, and treble. This is especially critical in professional-grade headphones with precisely engineered acoustic measures. And now you can see at the background we have some cover here and here. I hope you can see them. Yes. Why is the fabric-like cover? The fabric-like material visible over the driver is typically a protective grill or mesh layer made of the fabric, perforated metal, or vented plastic. This layer sits over the diaphragm and internal components of the driver. Why is it there? At the first, protection shields the diaphragm and voice coil from dust, moisture, and physical damage, such as airwaves intrusion or accidental pressure. And the second cause is acoustic control. The perforations and weave patterns of this layer help manage airflow and reduce unwanted vibration, minimizing sound distortion. And the last one is safety. Prevents user from directly touching sensitive internal parts like the magnet or voice coil, protecting both the components and the listener. This design serves both a technical purpose, acoustic optimization, and a practical role, durability and user safety. The next part is basket frame. The supporting structure that holds the driver together, typically made from plastic or lightweight metals like aluminum. This part must remain rigid and vibration-free to avoid introducing unwanted noise or distortion. And the last one is connecting wires right here and here. Yes, you can see it usually consists of positive lead red wire and negative lead black wire or ground connection. These wires transmit the electrical signal to the voice coil. So, how does a speaker work? You can see here, yes, you can see it. At the first, a speaker is an electromechanical transducer that converts electrical signals into sound waves. At the first, we have receiving the signal. Music is stored as a digital signal and converted to an analog signal by a DAC, digital to analog converter. The quality of the DAC directly affects sound clarity. This analog signal is then sent to the driver through wires, converting the signal into moment, the next step. Okay, the alternating current passing through the voice coil generates a force within the magnetic field of the parameter magnet according to Lorentz law. This force moves the voice coil back and forth producing sound. And the next step is producing sound. The movement of the voice coil causes the diaphragm to vibrate, displacing the surrounding air. This vibration progresses as sound waves, which our ears detect and our brains interpret as sound. And now we came to signal transmission chain in a headphone, as you can see here, right here. Okay, for sound to travel from your phone to your ears, the signal follows a specific path. At the first, we have a source. What is that? Phone or player. Music is stored digitally and converted into an analog signal via a DAC. The quality of the DAC significantly affects sound clarity. The next step is printed circuit board. In wireless or advanced headphones, a small PCB processes the signal. This board may include a monitor amplifier, ID filters, or even active noise cancellations ANC chips. And the next step is wires or wireless transmission. In wired headphones, the signal travels through copper wires to the driver. In wireless models, the signal is transmitted via Bluetooth or similar technology, which may slightly reduce quality due to compression. And the last step is driver. Finally, the signal reaches the voice coil of the driver, converting it into sound as explained above. And note, each of these stages can affect the final sound quality. For example, a poor quality DAC or noise interferences on the PCB may cause distortion. And now I want to show you as a picture right here, as you can see. Imagine we have a ID source here, a telephone or another things. Then we have a PCB printed circuit board, and then we have wires, and then driver, and we can hear our sounds. Okay, Wireless audio transmissions methods in wireless headphone technologies. At the first, we have Bluetooth. The most common method using 2.4 GHz, new versions 5 to 5.3 offer longer range up to 30 meters and lower power consumption. Advanced codes like aptX HD and LDAC improve audio quality. The next one is RF, radio frequency. Radio frequency uses higher frequencies, for example 9 MHz, with longer range up to 100 meters requiring a separator transmitter. And the next one is infrared. Light-based requiring direct line of sight, rare today. It used for a television in the past. And the last one is Wi-Fi, used in high-end headphones offering higher bandwidth ID, consumes more battery. And now we have to K wireless components. What are they? At the first, we have Bluetooth chip, the core of wireless technology, encoding and transmitting audio. New chips like Qualcomm Snapdragon Sound reduce latency, and improve sound. The next one is audio codecs. The codecs like SBC, AAC, aptX, and LDAC manage audio quality. LDAC transmits high-res audio up to 24 bit per 96 kHz, requiring device support. The next one is battery and charging. Lithium polymer batteries typically last 20 to 40 hours. Fast charging, 10 minutes charge for 5-hour playtime is common. And the last one is microphones and ANC. External microphones enable active noise cancellation ANC by detecting ambient sound and producing an inverted signal. So, why are some speakers louder and how it affects them? So, several factors determine how loud the speaker can get. At the first, we have diaphragm size. A larger diaphragm moves more air and can produce stronger, deeper sound, particularly in low frequencies, bass. And smaller diaphragms are limited in producing high volumes at high frequencies. And the next one is sensitivity. Sensitivity measured in decibels per milliwatt indicates how much sound a driver produces for a given input power. Drivers with high sensitivity, for example 100 to 110 decibel per milliwatt, generate louder sound with less power. For our drivers, sensitivity typically falls between 90 to 105 decibel per milliwatt depending on the design. The next one is input power heating. Drivers capable of handling higher power inputs like 50 milliwatt instead of 20 milliwatt can produce louder sound but require a more powerful amplifier. And the next one is housing design. The headphone housing can enhance or suppress sound waves. For example, closed-back housing enhances bass responses. Open-back housing offers a more natural sound but with less concentrated volume. And the last one is amplifier quality. What is that? If the source device, like a phone, has a weak built-in amplifier, even powerful drivers won't reach their full potential. And technical note, distortion. When a driver is pushed beyond its limits, such as at high volumes or extremely low frequencies, the diaphragms may fail to vibrate properly, causing distortion. This issue is more common in lower quality or smaller drivers. To minimize distortion, designers use premium materials like graphene and carefully engineered acoustic enclosure. Hope you find this explanation on headphone drivers and components helpful. I'd love to know which part you found most interesting or what topics you'd like us to cover next. Please share your thoughts in the comments and don't forget to like this video and subscribe to the channel so you won't miss future video engineering deep dives. Till next time, bye!